This is Karthikeyan Balasubramaniam, or Karthik for short. So let me first start by introducing the so we have a team from Argonne National Lab as well as Clemson University. From Argonne, we have Joshua, Omer, Felipe, who work on the Polaris side, and then myself, Karthik, I work on the grid side. From Clemson University, we have Professor Ali and Joshua, right? So it's a family team, and what we've been working on is, the title for this presentation is distribution transportation simulation using Polaris and OpenDSS, right? So let me get started. The overview of the presentation for today is going to be, initially we will spend quite a bit of time talking about the mapping. So these are all predictions for, years 2030, 2035, in 1 year, right? So predictions basically make sure, we need to make sure that it's in line with what is expected in reality. So that's what is going to be the start, beginning of this talk, right? The setup. We'll specifically talk about mapping. So this is mapping the geolocations available from the electrical assets to county level, county tract level information that we have, and then we build that up and project forward in time. Then we move on to the co-simulation studies itself. So we'll talk about two different approaches that we took. One is to have a one-directional information flow only from the transportation side to the grid simulator. So that means information will be flowing in about the EVs to the grid, but then if the grid is not able to support certain amount of EVs, charging requests, that feedback is not sent back to the transportation simulator. So that's going to be, one of the approaches. And then the other approach, we are going to look at the bidirectional information flow. So that's going to be two-way communication between both the simulators. Finally, we will look at some of the results that we have and talk about the conclusions. All right, so the first place we started was, we started looking for resources, right? And as I said, the mapping basically determines pretty much everything with regards to the results, because we could take the same scenario and then place a load in a non-optimal place and, show that things are going to be really bad, or we could do the exact opposite of that, or we could do things randomly, right? So getting this mapping right was of utmost importance to us, right? So the first thing we did was we looked at the resources that are available at Department of Transportation and also the AFTC website, where they have a lot of data, and then they link to all the other resources outside of AFTC as well. So some of them link back to the tools that are developed by the national labs, for example, EVA Pro and A-Fleet and stuff like that. And once we add that data, we have to go back and think, okay, we have this projection for, let's say, 5 years, 10 years, 15 years from now. How are we going to do the load allocation, right? Because, like I mentioned, if we know that certain amount of EVs are going to be coming online, in the next 10, 15 years, but how are we going to spread out the home charging loads across the distribution network that we have, right? So that was the first question. So we looked at what is the highest resolution data that we can get with, which is completely unrelated to the grid side of things, right? Which is going to be the census tract. So that's going to be a small area, which is about 1,200 to 4,000, people in it, right? And the census tracts do change over time. And the reason why I'm bringing this up is because we have fantastic open data sets with regards to information at census tract level, right? So it could be unemployment data, it could be, median household income data, and so on and so forth. So the question is, why is that important, right? That is important because now if we go back and look at the load allocation that we have, should we assume that every resident has an equal probability of, buying an EV like 5 years or 10 years from now? Or is that going to be related to, median household income and or an unemployment rate and other factors that, for which we have open data sets based on census tract level information, right? And the obvious answer is going to be, those are going to play a factor because more of the neighborhoods are likely to, to buy, EVs in the future than low-income neighborhoods, right? So that is the information that we wanted to map. So once we had that thought, we looked at the data at the census tract level. So when we go back and work with the utilities have data geolocation for, a lot of their assets, right? So these are electrical assets. Then the question becomes, how can we map this lat-long coordinates that belong to a set of feeders within the study area that is of interest to us, and do this load allocation, right? So the bottom, left bottom figure that you see as the representation of census tract is is something that I put together pretty recently to explain this load allocation problem, right? So imagine you have a small census tract, right? And then you have multiple feeders passing through it, and only a subset of the feeder nodes are actually belonging to that census tract, right? So then the load allocation problem is essentially figuring out what portion of the additional EV load that will come online in the next, n number of years should be allocated to the nodes within that region. So in this case, G1, G2, and R1. So that's the approach that we took. And there are two types of EV loads that can come online, right? So one is going to be from the EV charging stations, which are much more easier to map because that's going to be a one-to-one map. Either we have public chargers already available for which we know the location, or we are going to do some siting studies to add additional infrastructure for the future, right? What is difficult to map, and the ones that I talked about, is the home charging, right? So that's when we don't have much information with regards to which particular homes are likely residences likely to purchase an EV. That's where all this additional information that I talked about in the census tract level allows us to map that. And once we do that mapping, then we project forward in time to figure out how things are going to change over the next 10 or 15 years. So that being said, let's move on to the actual co-simulation studies itself, right? This is going to be a co-simulation between transportation and a distribution system. For the transportation, we have Polaris, and for the distribution side, we have OpenDSS. Polaris is a cross-platform software that can run on Linux tdc clusters. We do have Singularity containers, which we use. So one thing I want to mention is the problem that I will be discussing today is, can be described as an embarrassingly parallel problem, right? So that means for a given study area, we are interested in running this over a period of time, right? For example, we select high peak days within a given year, and then run the simulation, right? So if we can do every day solution, then essentially we can have this on day, right? So each day simulation will be run on one compute node, and that way we don't have to wait, a long time to have a lot of these analysis done, right? So that's why I mentioned them as embarrassingly parallel problems. So then we could also run this on a desktop if the study area is small enough. So then all of this is made possible by Helix, right? Because the co-simulation, there are two things that are needed. One is we need to pass the messages between the two simulators, and the other one is we need to ensure time synchronization, right? So we used everything from 5 minutes to 15 minutes to 1 hour resolution. So all this has to sync up in time. So the message queue that Helix uses allows us to do that, and that's what made this entire simulation possible. So then when we move on to the studies, we did this in 3 different phases, right? In phase 1, we essentially looked at one-directional information flow, and over here, this is purely an evaluation problem, right? So there is no control whatsoever from the grid side. There is no hardening of the distribution grid. It's simply a request coming in from the EVs, and then we are trying to satisfy that charging demand, right? Obviously, things are going to be, much worse in the particular scenario, and this represents a worst-case scenario, and we set it up that way, right? So then, with this phase 1, we can quantify the effects, but we don't do any mitigation now. So then we move to phase 2, which is the one-way, one-directional information flow, but over here we do updates on the grid side, right? For example, we may have a cap tank already sited, and we really increase the reading of that by 20 or 25%, right? And then we see what effects that might have, right? Essentially, what we are trying to get at is we want to focus our effort for this tool as an evaluation tool, as a cost-benefit analysis tool for the utilities and others as well, right? So then it becomes a question of what are the different strategies that we could use, and one of the best strategies would be improving the system that we have, right? So that's what phase 2 was all about, and then we move on to phase 3, where we now have bidirectional communication, and on top of all the things that we just talked about, we are going to have grid side optimization. So we could have this grid side optimization with or without the distribution system upgrades. And we have incentivized programs, which means we have flexible charging options, right? So maybe a EV decides I don't need to charge at at the highest possible rate. Maybe I'm flexible. So in that case, they will be presented with options for lesser dollar per kilowatt hour, just so the rate of charging is flexible. So all those kind of things basically leads to multi-period problem. Right? So multi-period problem can be formulated from the grid side as an MILP problem, but then it be the assumption that efficiency should be modeled within the battery, in the battery model. Then you can actually model the entire thing as a LP problem, which is much more nicer. So both options are possible. We have tried out both of those different versions. Finally, not all charging can be accommodated. Right? So once we go to flexible charging, there is a small probability that not all EV charging requests can be accommodated. So when that happens, the information from the grid side goes back to Polaris, and Polaris will build its own unit based on that information. And the evolution of that course information from that point on will diverge compared to the one directional information case, right? So that's overall, quick update about all the three phases of studies that we did. Then we moved on to, let's look at how the load composition is going to be, right? So we are projecting an increase in load, as we move forward in the future, right? That could come from two different places. So everything other than EV is grouped into a category called non-EV load growth, and everything EV is going to be EV load growth, right? So once we do that, then we can basically set up the studies in different ways for all the three phases, right? So we could have low, moderate, or high level of adoption for EVs, and similarly low, moderate, or high level increase in non-EV load growth. And the combination of that is what we studied.
So Karthik, you've got about 2 minutes.
All right. So let me move quickly to the results. So this is one of the results. This has like millions of data points. What we did was we took 2 peak from every year, every month of the year that we are going to study. And remember, this is a study that we did for every year from the base case 2021 all the way to 2025, right? So we have about 24 days of simulation for every year. This is just for the base case 2030 and 2035, but then we have the results for every year, like I mentioned. So then, on the left side, you're seeing phase one, which is the histogram of all the voltage magnitudes across all the phases, within the study area, which is Bloomington, Illinois. And as expected, this is going to be the worst case scenario because we haven't hardened the system, right? So that means unit have, as we go forward in time, you're going to have more and more incidences of low voltage currents, as you see on the left side of the plot, right? So then the question is, okay, what if we allow a random upgrade of the system that we already have, for instance, gap banks, and we allow them to be sized up to 25% larger than what they are currently at the base case, right? So once we allow that, a lot of things, a lot of the issues that we saw previously on the left side figure actually went away, right? So does this mean, just increasing some of the existing equipment size would work wonders? The answer is no, and that is illustrated in this chart, right? So this is a histogram of the line currents that you're seeing. Again, millions of data points, same method of phase one and phase two, and what you're seeing is if you have increased load, you have to have increased line current, right? There's no way around it. The only way that that can be mitigated is if we are able to do flexible charging, right? So if you're able to do optimization with regards to the consumption pattern, that will change the consumption pattern. Then the loading on each line can be reduced, comparatively, right? And that's essentially a phase three, right? Which is what I explained previously. I don't have the results yet for the phase three. That's still a work in progress. But that's how we have structured this, right? So essentially, you start with just an evaluation, then you move to system upgrades, and then you move to phase three, which is system upgrades plus optimization from the distribution side, or just the optimization without the system upgrade. So that way, we're able to do a cost-benefit analysis, hero utility, you have all the assets information, right? You do the mapping, and then you go back and run the different phases to get a clear indication of where the focus needs to be as we move forward in time with with the uptick in EV adoption. And finally, the question.
Okay, perfect. Yep. Time's up. So we won't have time for questions. Go ahead and wrap up.
All right. Yeah. So just one final note. Shout out to all the developers for Helix, OpenDSS, Polaris, and a bunch of other open source software that we use, which made this entire study possible. So with that, I'll be happy to answer any questions you might have.
Thanks so much, Karthik. Yeah, we've got about 8 minutes for questions. We're trying to finish a few minutes before the top of the hour so folks can get on with what else they've got going on. So feel free to raise your hand or put questions in chat. Looks like Jean has a question.
Is this, thanks, Brian. Is this the Polaris open source tool, or is made by your lab?
Yeah, that's a good question. Yeah, so there is an open source version of this, that's available on GitHub. And then some of the additional features that we added, that is not yet open source. But yes, to answer your question, yes, it's available in GitHub.
Sorry, your voice, I couldn't hear very well.
Oh.
You said it's available for public to use, or?
Yes, that's right. So there is a public version available in GitHub that is open source. Some of the new features that we added, like the bidirectional communication that I talked about, that is not yet there as open source, but the software itself, almost 95% of the features is already available in the open source version. Yeah.
Okay. Thank you.
Yeah, my apologies. My microphone is not working well, so I had to dial in. So that's why if you're having audio issues, kindly let me know.
Okay, that's fine. Thank you.
Yeah, thanks. Looks like Andrew's got a question.
Yeah, thanks. Nice presentation. I guess I'm kind of curious around like infrastructure deployment scenarios when it comes to EV charging stations. Like not all locations, most locations EVs park are not serviced by charging equipment. And so I'm kind of curious how you take that into account in the reformulation within Polaris.
Yeah, thanks for the question. Yeah, so we had to make some certain level of assumptions, right? So right now, I think there are about 60,000 something charging stations, all across the entire US, right? With about 150K, ports available. So the projections that we made within the study area is based on the current density of, charging stations. So then we took two approaches, right? One is adding additional ports to the existing infrastructure. That means we already know where the charging stations are located, so the load allocation problem that I talked about goes away, right? And the other approach is essentially to say we have to add additional, charging infrastructure as we move forward in time, and that was done, simply based on voltage studies, right? So any place that is most susceptible to voltage issues, we avoided those nodes and we placed them at other nodes, and that's how we did the mapping on the electrical grid side. As far as the transportation side is concerned, once we did this, did this approach, then we convey that information back to the transportation system where, where the number of chargers would increase, the number of EVs would increase, and so on and so forth. So that's how we did it. I don't know if I answered the exact question that you had, but I hope I answered at least some part of it.
Yeah, thank you.
Okay, thanks. It looks like there's a question in chat from Gitao. I'm not sorry if I'm saying that incorrectly. Looking for a link that maybe you could put in the chat for Polaris. Yeah.
Sorry, Brian, could you say that again? Sorry, I didn't catch you there.
Oh, there's just a comment, a question in chat that's more of a looking for the link for either the source code or executable for Polaris. So if you have a chance,
sure.
You could pop it in there. We're wrapped up.
Yes, I will post it in the chat, right away. Yeah.
Cool. I actually had a couple of questions for you too. The first was with a lot of these transportation models, there's certainly a ton of data on the transportation side. Is Polaris, my understanding is that a lot of the data for that is currently in the Chicago area, is that right? Or are there multiple areas covered, or how does that work?
Yeah, so the study area that is presented today is Bloomington, Illinois. It's a pretty small area, about 25 or so square miles. So that's the area that we focused on, just to get things right. Yeah.
Cool. And then, like, if people have access within this open source Polaris tool, does that provide data for other places, or does that include data for those, or is that sort of a bring your own data kind of open tool?
Yeah, I would have to get back to you on that. I'm not sure. So I just use this one, which I assume comes with Polaris, but I would have to double check. But this Bloomington, I believe, is an open data set. But for other areas, I'm not really sure. But it might be an open data set. So let me get back to you on that.
Cool. Yeah, no, that's great. And then I have another data question, this time on the grid side. You mentioned using some open data sets. I saw a few pictures that were showing like IEEE 123. I was wondering which kind of feeder data you were using within your mapping effort.
Yeah, so we used, obviously we used 123 node, we used the 8500 node, from IEEE data sets. We also used the SmartDS feeders, which you guys used, for the other studies, right? So it's a combination of these, and the reason why we had to use that is because we wanted to keep, the data open, use the open data set, so that way somebody else can, just, right? So that means everything is synthetic data, right? So we don't have any geo coordinates; it doesn't belong to that particular region, but we had to map that, artificially to fit within that region. So, yes, so it's a combination of different feeders, all the way from 123 node feeder to the SmartDS. I think the largest SmartDS feeder that we use, there is a ton of feeders in SmartDS, right? I think we used about one which is close to 9,000 nodes, 8,600 nodes or something. So yeah, so it's a combination of those.
Cool. Yeah, so that's where you had to do the mapping, because the SmartDS stuff is geolocated to other parts of the country, so you had to sort of remap it. Yeah, that's cool. Yeah, thanks. Any other questions for Karthik? Sort of last one before we wrap up. Okay, well, please join me in thanking both of our presenters, both Nadia and Karthik. Some really interesting work here on the grid and transportation space. Thanks so much, and looking forward to seeing folks next week. Let me quickly share the schedule there. Come on, share. Next week, we will have presentations from Brian Sergi and Karthik again, and this time around the electric power system and the natural gas co-simulation. Hope everyone's able to join then. And if people have other questions or chats, feel free to reach out to our presenters today, and or put something in the chat window, which at least for a little while people are still connected, should stay available. And with that, I'm going to go ahead and stop the recording.